Okay, so what I wanted to do today is kind of give you a broad introduction to GeoDa. I'm assuming you have downloaded it and installed it. If not, you should do that as soon as possible. And I realized, sorry, this is all very last minute. I realized that there's actually very few videos out there with actual GeoDa demonstrations. There's lots of notebooks, lots of web pages. There's documentation on the GeoDa site, but actual videos, live things, there's the video that I gave you the link to on Monday, which is kind of a sales pitch, but there's not actual lab materials. So I figured I might as well record this. So then you can look it over at your leisure or not, you know. But I don't know, I forgot if I mentioned this or not, but there is a whole collection of materials under the channel GeoDa Center on YouTube. You know, we're having hundreds of thousands of views. These are old lectures of mine in my introduction to spatial data science, but it doesn't have the labs. It's just the lectures. And then also my more advanced spatial regression class and a spatial clustering class. And then all kinds of different talks. It's all up there, you know. If you ever get bored, you can take a look. And so that's what I'm going to do with these. I have, I think, 6 sets of lab really demonstrations, and then give you a chance to practice and see if you get it to work. The idea is to not dwell on the mechanics too much, just a little bit, so you can get going. But the main idea is to give you a tool that you can use to explore spatial data. And I'm assuming, and I know that most of you have never done this. And so this is part of the reason why we have this spatial track in the core to kind of get you going. And so this, I want to emphasize this, the goal here is not, you know, kind of a hazing routine, which I know some of the core classes are kind of like that or feel that way. I want you to start thinking about the world a little bit different. You know, as there's a commercial slogan, the why of where, right? So you start thinking about phenomena, where they are located, and why things are where they are, or why they're not where you thought they should be. And that perspective is what I call spatial thinking. And so we'll get there by doing different readings and see how other people think about it. But also, I think very important, get your hands dirty, look at some actual spatial data, make some maps, do some fairly, you know, straightforward analyses. This is not rocket science. There is complicated math behind it, but we won't go there. I will focus on the concepts and on the kind of insights that you can gain by doing this. That's the main goal. Okay. So the GeoDa, if you have installed it, you just make sure it's the latest version. You open it, whatever your operating system does. And now it's not playing nice. Why not? I don't know. There we go. Okay. So can everybody see this? So ideally, you know, you're in your own operating system. I honestly can't remember how it's done in Windows, but I'm sure it's just as simple. This is the toolbar. Every icon on the toolbar corresponds to a subset of functionality. you have the same subset here in the file menu. So you have an icon to open a data set. You have file and new data set or open project the same way, right? So what I want to show you first is I'm going to open the file. So you see here recent. Those are the files I recently opened, and I'm going to close them. And then you see sample data. These are baked into GeoDa. So they are already there. If you select one of these, double click on it, and it opens up. So anytime you open a geographic file, all these are geographic files, it opens a green base map, what I call a themeless base map. So this example is the 77 community areas of Chicago. These go back, in fact, you'll have a reading about this when we read about neighborhoods. This goes back to the Chicago School of Sociology in the 1930s. They delineated these. They haven't changed. Now, this is almost 100 years ago. They haven't changed. Is that appropriate? That's a different question. But there's 77 of them. It says it right there, right? And it also says it here at the bottom. Okay. So this is a map. I'll talk a little bit about maps today, not too much. We'll have a whole lab devoted to maps in its own right. I just want to kind of walk around and show you the different functionality, very high end view, and then I want to show you a few things that you do in terms of non-spatial data wrangling. So manipulating data in a table is very simple stuff. It's the kind of things you do in Excel or another spreadsheet, selecting observations, selecting variables, changing variable names, changing the format of variables. This is, as I said, this is not rocket science, but there's a certain way in which it's done in GeoDa. And the more that is familiar, the faster you're going to work, right? The first time, and I always have to catch myself, because if I go through this, I go click, 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 and I'm done, right? If you've never seen this before, you have no idea what I did, right? So I'm going to try to pace myself and show the different icons and what they do. And then as you get more familiar with this, you'll be in the click, click, click world as well. And then you'll find, and I know this is advertising, GeoDa is a very efficient tool to explore spatial data. I use it myself all the time. Everything I've ever needed for my research is in GeoDa. It's now been around almost 20 years, but it's completely changed. It's cross-platform. It runs on everything. It's open source. You can look at the source code. If you're a computer science major, might want to take a look. It's C++. This is not for the faint of heart, but it's very fast and very efficient. Okay. The new version, which if I have extra time, I'll run a little demo, is written in JavaScript calling C++. And so we're in the process of moving everything over to a JavaScript interface. This interface, for those of you techies, is WX Widgets. WX Widgets was one of the first cross-platform GUI engine. I mean, now you have several. Qt is a popular one that you may be familiar with. WX Widgets is still being developed. But when we started porting things, it was originally a Windows-only program. And then I started the whole open sourcing of it. And then we found WX Widgets at the time had the best support in that 98% of the code is exactly the same on Windows, on Mac, on Linux. So that's hugely efficient, which typically, if you get into the C and the C++ world, is not necessarily the case. Okay, so that's a little bit of history. Now, the design of GeoDa is on purpose. It's, you know, kind of follows the way I think about data exploration. And it starts with very simple stuff, data manipulation, simple, straightforward visualization of spatial data in terms of maps, different kinds of maps, some maps you won't find anywhere else, and then statistical graphs. And these are pretty standard, nothing that we invented. It's all pretty standard stuff, which you may already, if you took a visualization class or a statistical graphics class, you're probably familiar with that. And then we get in more of the technical part. We go from the simple exploration and get into the notion of spatial autocorrelation, which is quite complex, but I'll deal with it. I'll try to deal with it at a fairly intuitive level, skip the math, give you a sense of what it is and some of the visualization devices that were original to GeoDa that some other software has it too now, that allow you to visualize spatial autocorrelation and its local version of it, which allows you to detect clusters. And that's probably the most powerful aspect in an exploratory sense of GeoDa, is the exploration of clusters. And there's two types of clusters. One is statistical clusters. That's where we're going to stick to for this class. Another one is clustering, more in a data science kind of concept. You know, you may be familiar with k-means or hierarchical clustering or things of that. We have all that, but also spatially constrained clustering, which not too many people have, where we impose the grouping together of observations that are not only similar in a multivariate sense in terms of the multiple variables, but also connect to each other, our neighbors. And that's a very complex optimization problem. And so that's in here as well. And then there's a little bit of spatial regression analysis, but it's a subset of the real deal, so to speak, which is in the PyCell Python library module SPREC, which I'm still working on actively. So that's kind of the progression. You start by getting the data in front of you, thinking, what is my research question? How can I actually visualize this? How can I find interesting patterns or patterns that I think might be interesting? And then gradually you get more and more refined into formalizing, are these patterns for real or are these just figments of my imagination? Because the human brain is wired to recognize patterns. So you see patterns whether they're there or not. Okay, so one thing I never want you to do is you make a map and you stand there and you say, I see a cluster here. You may see a cluster, that doesn't mean there is a cluster. And so one of the things we're going to accomplish is get to techniques where you can actually establish, is this something that has structure beyond what I could expect by accident? Accident will be called spatial randomness. Spatial randomness means it doesn't matter where things occur. We don't care about that. We're not interested in that. We're interested in spatial structure, in spatial patterns. So it's actually a two-step process. The first step is identifying the patterns, which is what we're going to do in this class. The next step, which is much more complicated, is explaining the patterns. Why are things where they are? So that's kind of the progression. So each of these kind of large conceptual areas corresponds to an icon on the bar. And you can, if you just wait a little second, it will pop up a little window below it, which will tell you what this particular functionality is. So this is to open files. We just did this. This is to close files. This is to save files. Okay. This is a table functionality, and we'll spend a little bit of time on that today. So every spatial data set consists of two things. One is the data. You know that. Already know how to do that. A spreadsheet has the data. Rows are observations, columns are variables, right? What spatial data have that a spreadsheet doesn't have is the information about the location. So you have a spreadsheet with community areas. You don't know whether that community area is in the north, the south, or the west, or in the loop, right? That information is this information. So that's a second characteristic of spatial data. Now, how do we get this, right? So think about this for a second. How do you know where something is? Any suggestions?
You measure its distance or Euclidean distance from a certain origin that you pick.
That is excellent for a point, but how about a community area? Is this kind of zone? Anybody has done analytical geometry in high school? No? So it's not rocket science. It's actually fun, That's what is happening in computer graphics under the hood. How do you know whether two lines intersect? Where do they intersect? You solve a system of equations, and that gives you the coordinates as the result. So you can pinpoint every location in 2 dimensions by the x coordinate and the y coordinate. So those are the coordinates. So every point can be located on a map with just x and y. That's all you need. Now, what about an area? How would you do that?
Well, like connect the corners of a region by line segments, and then the area would be the region within them.
So I think you have 90+% of the answer. So line segments is the key. So these are not actually lines, but they're approximated by lines. So you simplify the actual outline of the border by a series of line segments, and every line segment can be defined by its begin point and end point. It's a line. You don't need to know, begin point and slope will get you there too, but then you don't know how far it goes. Begin point and end point gives you all the information you need to locate the line in 2 dimensions. So each of these areas, we call them polygons, are stored as sequences of coordinates of line segments. That is the spatial information. That's how we know where things are. And a spreadsheet can't do that. A spreadsheet can store X and Y, but once you get to irregular units, they don't all have the same number of segments. So it doesn't fit in the rectangular table format. It's a separate kind of data format. In database speak, it's called a blob, because it has a structure, but the structure is not the same for each observation. And so the difference between non-spatial data and spatial data is that in spatial data, every observation is tied to a specific location. And that location can be a point, or in most of our examples, that location will be an area. And so then if you manipulate the data in the table, you always know where this observation is, in this case, on the map. And I'll show you that in a few minutes. So the table has the actual data. If I click on this, you see it's just like a spreadsheet, variables and observations, okay? This next group is tools. These are practical data wrangling tools to create spatial data. For example, if you have a table with X and Y coordinates, it will turn it into a point map. If you want a regular grid, squares or rectangles, you specify the corners, how many grids you want, and it will create it for you. So those are very practical tools that you may or may not end up using. This is the weights manager, which pertains to spatial weights. Spatial weights are something very complicated. I mean, they're actually not, but it's a complex concept, is the way you define the connectedness between the observations. So we'll be talking about that when we talk about spatial autocorrelation. How do you find a neighbor relation? One way in which you can define a neighbor relation is, say, two areas have a common boundary, or they are within a given distance of each other. You know, those kinds of things define, if you wish, a network structure where observations are the nodes and the connections between the nodes are the neighbor relation. And that is stored in a spatial weights matrix. This is the mapping functionality. We will see this in a couple of weeks, all kinds of different maps that we can make. A special map is called a cartogram. This is a way of animating the map, and this is a way of customizing the legend for a map. I don't know how much time I'm going to have to talk about this, but I do want you to have just a basic skill set to make some decent looking maps. And then some of these maps are really what I call statistical maps, in that they are not just giving you a pretty picture, but they also are providing statistical information on the distribution of the data. So that's something that GeoDa has, and much other standard mapping software typically doesn't have this. Then we go into what is called EDA, or exploratory data analysis, which is visualization. That's a big part of data science. We see all the classic graphs, histograms, box plots, scatter plot with regression lines, scatter plot matrix, bubble chart, 3D scatter plot, parallel coordinate plot, conditional plot, you know, all these things that allow you to visualize multivariate data, more than one variable. Who's familiar with parallel coordinate plots? Okay, so that's the usual. So I will talk about it because it's a very powerful tool. This is the cluster analysis I told you about. K-means, hierarchical clustering, spatially constrained clustering. This is global spatial autocorrelation, characterizing a whole map with one coefficient. And this is another form of global spatial autocorrelation, the parallelogram. This is local spatial autocorrelation or cluster maps. This will be the main focus of our analysis, is how to create these maps, how to interpret them, how to identify spatial clusters in variables. And of course, then the next step is, if there are clusters, why are they there? Why are they where they are? And we won't go there. That's what you do in spatial modeling. Okay? For example, you find that all the high poverty areas are in the same part of the city. In a spatially random world, that should not be the case. You know, all the people who vote for a particular candidate live in the same part of the country. In a spatially random world, that should not be the case. It shouldn't matter where you are, how you vote. In reality, it does, very much so. So the first step is first identifying those clusters, and then the next step is, why are they there? Why isn't it the same everywhere? And then we have some time things and the regression. We won't really talk about that. So any questions at this point?